Thank you very much. And thank you for having me back. It was fun to be here in, when was that, May or April? Something. Was it May? Maybe. It wasn't that long ago. So it's nice to be back again. And thank you for suggesting survival, because when we were talking about possible topics, I was going to be in town this week anyway. And so I offered to come back over because I thought it would be fun. But I didn't have another topic. And Ariel suggested, or maybe Patrick, somebody suggested survival, which is fun for me because A, I don't do it much anymore, and B, it's actually how I came to Stata, to using Stata. About 20 years ago, I was a SAS user working in clinical trials, and we did a lot of Cox regression with time-dependent covariates. And at the time, Stata had just released a really nice routine for doing Cox with time-dependent covariates, and it ran way faster than proc-phreg did in SAS. And so a group of us started using Stata just for that. We were using SAS for everything, but when we wanted time-varying covariates, we'd go use Stata. But over time, I and other people in the group started liking Stata so much that we kind of migrated over to Stata. And 20 years later, I now work for the company. So it's kind of a fun, long road. So the unfortunate thing is I don't do a lot of survival analysis anymore, so this is a good excuse for me to get back into it. The other thing, you're my guinea pig. I've not done this talk before. I put this together last week, and I don't know what ended up being in the abstract that was sent around, but that abstract was way too ambitious. There were a ton of things in there. It was basically 2 semesters of survival analysis that I thought I was going to cram into an hour. So what I'm actually going to talk about in this first hour, because we have 2 hours, right? We have this hour, and then we'll take a little break and come back. I'm just going to go through the basics in this talk today. So I'm going to assume that you may or may not be very familiar with survival analysis. So we'll just touch on the jargon and stuff at the beginning, but we'll move through that quickly. And then I just want to go through non-parametric, semi-parametric, and parametric estimation in this first hour, just to become familiar with maybe how to do it or just how to do it in Stata. And if it's too boring and I'm way off topic, you guys throw something at me and we'll go off script if we need to. Then I'm going to come back next hour and talk about some variations of these things for special cases. So we'll have Cox regression with time-dependent covariates, categorical covariates, continuous covariates. What else? Frailty models, multi-level survival models, and then a bit on competing risks regression. The one thing I didn't include that you just mentioned was treatment effect survival. I can't believe I didn't put that in here. So we can talk about that.
Multiple outcomes.
Well, that's the competing risks.
Oh,
you're talking about multiple outcomes where you
might have the event occur more than once, like repeated hospitalization, let's say.
That's in here with the frailty stuff.
Okay.
I think it is. Okay, so this is where we're going today. And if you have any questions, comments, suggestions, I'd much rather talk back and forth than me just talk solid for a whole hour. It gives me a chance to catch my breath and grab some water once in a while. So just jump in anytime and we'll have a conversation about this. A lot of what I'm going to talk about today comes from this book called Intro to Survival Analysis Using Stata that was written by Mario Clevis, Bill Gould, who's the founder of Stata Corp, and Yulia Marchenko. I know I work for the company, so I'm biased, but I really like this book. And if you want to learn about survival analysis in general and survival analysis in Stata in particular, this is a really great resource. So a lot of what I'm going to show you today is based on what's in this book. So let's get on with the topic. So survival analysis, what is this anyway? Why does it get its own class in most departments, and why is it considered its own sort of small branch of statistics? Well, its primary focus is the amount of time it takes to wait until some event occurs. So it's time-based. How long do I have to wait until something occurs? And so sometimes it's called time-to-event data. In the biomedical sciences, we typically call it survival analysis because we're usually waiting on people to do something, die, or have heart attacks or things like that. But in industry, people use this to model light bulb failures. Or what's the other one? Economists use this to measure time that people are unemployed until they get a new job. So it's not just about survival, even though we tend to call it survival analysis. It has uses outside of that. So these are some examples. Now, the other thing that makes survival analysis unique is something called censoring. So we don't always observe the event that we're waiting for. So we wait, the person just won't die, or they won't have that heart attack or whatever. I know it's morbid, but, as analysts, we're a little weird that way. So they never have the event while we're watching them. And so if they don't have we wait, but they never have the event, we call that censoring. We know they didn't have the event up until the time we stopped watching them, but we don't know if they ever had the event. In the case of death, we do. They will eventually have to die. We just don't know when. So this is what typical survival data looks like. This data set has the ID called number. Just think of number as ID, it's just the person. So we usually have two variables. We need at least these two variables if we have censoring. The first thing we need is years. Can you see that in the back of the room? Okay, so the first part of the outcome we have is years, which is the time until something occurred. And then we have their status. Did the person die or were they censored? And I've tried to represent this graphically on the right because I think it makes a little bit more sense. So for example, person 1 here made it to a year, but then they died. And so I've represented the fact that they died by putting a little red X and making their line red, so I know that that person made it that far and then they died. Person number 2 here made it 12.3 years and they didn't die. They were censored. So I've drawn this one in green with a little circle to indicate that person was censored. We know they're eventually going to die. They just didn't die while we were watching them. And so we have a collection of of data like this, and we like to analyze that in some fashion. Okay? So I don't want to dwell on this because usually what we see is right censoring, but there are 3 kinds of censoring: right, interval, and left censoring. And what this refers to is, let's say that I'm following a person over time moving from left to right, and I begin observing them at some point, and I stop watching someone at some point. If the failure event that I'm interested in occurs after I stop observing them, then I refer to that as right censored, because as I'm going across in time, it's to the right of when I stop observing them. So that's right censoring. There are a variety of reasons why this can occur. You can imagine your own, I'm sure. You run out of money and you just can't keep following them or whatever. Interval censoring, on the other hand, means that I start watching the person and the failure event occurs, but I don't know exactly where, and then I stop observing them. And at the end, I know that the event occurred somewhere in there, but I don't know exactly where. And probably the most common example of this is silent MI, silent myocardial infarction. People think they had bad indigestion. And in fact, it wasn't bad indigestion. They had a mild MI, but they didn't know it. And they don't remember the exact day. So between 2 physician visits or 2 observation points, you know that the event happened somewhere in there. You just don't know the exact time. So that would be called interval censoring. Then lastly, you could have something called left censoring. So say you're out recruiting people and you're recruiting for your study. Death, you would generally know, but there may be other things that happen before you officially start observing someone or treating them in a clinical trial. And the event happens before you start observing them officially. That would be considered left censoring. The thing we typically deal with is right censoring because we just don't have enough money and time to follow these people forever. So if this doesn't make a lot of sense, don't worry about it. Right censoring is the thing we typically deal with. The data set that I'm going to use for this first hour is a very popular data set called the PBC data set. It's, I'm afraid to even try to pronounce this, but it's primary biliary cirrhosis. That's not so bad. It's the treatment. And D-penicillamine, DPCA is the treatment. So I have this liver disease, and I have a treatment for this disease. So I have some folks who are treated and some folks who are controlled. And I want to see how long these people go before they die. So I had 154 people in the treatment group, 158 people in the control group. And I'm going to follow these people over time and see, are their death experiences different for the treatment in the control group. I mentioned this book because they didn't collect this data, I don't think, but I got the data from their website. And if you want to go grab this data, it's not one of our official data sets, but you can grab it off one of the author's websites right here. And I'll be happy to make these slides available if you guys want, so you can grab this stuff and the do files and so forth. So the first thing that I want to do with this data set is open it up and just take a look and see what's in here. I haven't listed everything. There are more variables, but these are the ones I'm really interested in for today. I have the case number, which is called number instead of ID, but that's the ID. I have years, which is a variable for time to death, measured in years. I have their status, whether this person is alive or dead when I'm done watching them. I have their age, I have their sex, and then I have a variable called RX, which is their treatment, whether they're part of the treatment group or the control group. The first thing in Stata, I don't think you do this in SAS. It's been 20 years since I've done this in SAS, so they may have changed it. But in Stata, you can tell Stata that you're going to be using survival data by using the stset command. So stset, the way this works is you type stset, you tell it the time variable, which in this case is years, and then you type comma failure, and you tell Stata what the failure variable is, what's the indicator for death or censored. And in this case, just to be on the safe side, I've used the scale 1 variable, meaning the scale of time is 1 year. You don't have to put that in there, but it's kind of a habit for me, and it's not a bad thing to do. To tell it what the unit scale is that you want to use for the denominator, events per whatever. Okay, so after I use the survey set command, there's the laser pointer work. After I use the survey set command, Stata creates some variables that it's going to be using under the hood. I call it under the hood, behind the scenes, where you don't necessarily see it. But these variables are created and put in the data set for you. _ST is whether or not this record is to be used at all. Generally, all the records will be used, so that one's not terribly important. _D is the failure variable. That's the indicator for whether the person had the event or not, okay? And that's what Stata is going to use when it runs stcox and all these other fancy commands. It's going to use that. It's not going to use your variable, your original variable, and I'll show you why in the next hour, because there are some things that make this more complicated. Then the analysis time, _T is the analysis time when the record ends. _T0 is when the record begins, because we need to know when we started watching them and when we stopped. And you can customize all of these things. I don't want to dwell on this too much, but those are the actual variables that Stata will be using to do the calculations. So if I look at my original data, I have the number, the status, and years. Those perfectly match, in this case, to D and T, and T0, okay? So for instance, person number 1 here, they started at time 0, they ended observation at 1.1, which is how many years they were followed. _D is 1, which indicates that they died, okay? So for a simple data set like this, there's a one-to-one correspondence between status and time and years, years and time and status and _D. So let's look at some things that we might want to do with this data set. I want to start off with non-parametric estimation. And I have to confess, I'm not sure I want to say this on recording, but I will. I came to survival analysis from a clinical trials perspective. And we did a lot of Cox regression, because there were things, even though they were largely allocated, randomly allocated to treatment groups and so forth, we still wanted to adjust for things like age and some other things just to be sure. And so I used to have this bias that everything ended up going through Cox regression. We just sort of jumped to that and skipped over a lot of the basics. And so when I was at Texas A&M, I used to teach survival analysis as part of another class. And so I really kind of ignored a lot of the non-parametric stuff, which in retrospect, now that I'm a little older and wiser, these are actually really useful commands here at the top, and I wouldn't just race past them. So I do want to spend a little bit of time on this. There's some fun things you can do with non-parametric estimation where you're not imposing any kind of models or assumptions on them. So if you're like me and you just race past these, you might want to pause and back up. So for instance, we might just want to look at what is the incidence rate in the two groups. That seems like a logical thing to do. So there's a command in Stata called STIR for survival time incidence rate, and you just tell it the name of the treatment variable, and it will tell you the number of failures in the exposed group. Here, exposed is who is exposed to the treatment, the number of failures or deaths in the unexposed group or the placebo group, and then it will add up the total amount of time that these people were watched. All of those times get added together, and so we have the number of failures per time, which gives us an incidence rate. So if we look at these incidence rates, we can see that we have about 0.07 failures per day, I guess would be the interpretation of that. So that would be, what, we need about 12, 13 failures, no, 12, 13 days to observe one failure. Is that what that works out to be? Something like that. There's some other things you can get, such as incidence rate differences and ratios and things like that, but sometimes it's better to just start simple and just get an incidence rate for these. And the incidence rate looks a little bit higher in the unexposed group. So maybe our treatment is working, maybe it's not, but this is a first clue. So that's something we might want to take a look at. Good old life tables. This is something I really used to ignore. It turns out health departments across the world still publish these things. And if you go to the World Health Organization website, they publish these kinds of things. So there's more to life than Cox regression, I guess is my mistake. I'm trying to not encourage you to make the same thing by making this all about Cox regression, which is my tendency. So we can talk about life tables. So for instance, this first row here, we have the interval 0 to 1 days. Wait, this was in years. Years, I'm sorry, I keep saying days. This one's measured in years. Next hour is days. So we have the interval 0 to 1 year. We started off with 312 people. We observed 22 deaths. We lost 0 people. Lost meaning people wander off. They sign up for your study and they move away or they drop out or whatever. So we didn't lose anyone in the first year. So 92.95% survived, 0.9295. We can put a standard error on that. We can put a confidence interval on it. So that's something that is often done and can be useful. Okay. What's even more useful is if we do this by the placebo group and the treatment group. So here we can see that in the first 2 years, 91% survived in the placebo group, 87%, 88 if you round it, survived in the treatment group. Oh, you should scratch your head. I thought the treatment was supposed to help these people survive longer. But anyway, it's again a first pass where we're not imposing any kind of models. We're not doing a lot of assumptions, making a lot of assumptions with this. We're just kind of looking at the data and getting to know it. Another thing that's popular are Kaplan-Meier curves. This just is a really basic graph. On the horizontal axis, we have time, and on the vertical axis, we have the probability of surviving up until a certain point in time. So at time 0, everyone is still alive. At time 1 year, a certain proportion, I don't have 1 on here, but at 5 years, we can go up to this graph and see that about 70% of the folks were still alive. And I actually did a little graph here that makes it easier to see. These Kaplan-Meier curves allow us to make statements such as the probability of a patient being alive after 60 days after diagnosis is roughly 45%. Okay? So that's what these graphs are kind of useful for. You can do the same thing with a life table. What's the probability that someone in the placebo group makes it out to 8 years is about 53, 54%. You can do that. But these graphs sometimes make it a little easier to see. You can also do these Kaplan-Meier curves by the treated and control group. And here we see that it's a little bit more complicated. If we look at the graphs, we see that in the beginning, remember before the incidence rate looked like it was a little lower in the treatment, the incidence rate is a little bit lower higher in the treatment group. But then we go to the life tables, and it looks like survival at the end of the first year is worse for the treatment group than it is for the placebo. But the nice thing about these Kaplan-Meier curves is we can start to see a much more complex pattern here. So in the beginning, right out of the gate, it looks like the treated folks are dying off a little bit faster, okay, because the red line is the treated group, and they're falling off a little quicker. Their survival curve is dipping down faster. But then somewhere along about 5 years, if you make it out to 5 years, it looks like the treated group actually does better, and then they kind of cross back again here. The reality is if you put a confidence band around these, there's really not that big of a difference. So that's something you would definitely want to look at is, okay, they're crisscrossing, but are they within the 95% confidence interval? But these do allow you to have a bit more sophisticated look at what's going on as opposed to just an incidence rate or a life table. There is another thing called the Kaplan-Meier estimator, which allows us to look at things at instantaneous time. So rather than looking at an interval of 0 to 1 year, we can say what's the probability of failure at 1 year, 2 years, or whatever. I have some, and we can do this by treatment group as well. It's another kind of life table, but it's a slightly different way of looking at it. Time is considered instantaneous, and I have all these slides that I was going to go through, but I don't think I have time, that shows you how the calculations are done. Left those in from my old class notes. So that's another way of looking at life tables. It's non-parametric. You're not imposing any kind of a structure on it. The last non-parametric thing I want to talk about is the log rank test. For clinical trials, if you have a completely randomized clinical trial and you believe that everything was sort of washed out nicely, there's no reason for your final test statistic to just be a log rank test. Okay, so you could just test whether the survival experience was different for the treatment or placebo group. We get a p-value from it, and away we go. In this case, the p-value is 0.7498, so that would suggest that the treatment was not effective. Now, the downside of this is it doesn't take into account other covariates. If we look back at that, way back through all these slides again, we have this sort of complex pattern going on over time, and the log rank test doesn't really capture that very well. But nonetheless, if we had well-behaved, nicely randomized data, log rank test is a perfectly good way to end off your analysis for your clinical trial. Treatment didn't work. Okay. So I have how you do the calculations in here because it's kind of fun. It's a Mantel-Hansel-like thing. But again, in the interest of time, I think we'll just go along past that. Any questions so far with the non-parametric stuff?
Just a real quick statement about so the log rank table is fine if you did a randomized control.
Yes. And the randomization worked pretty well. You
yeah,
kind of checked
in. What about the, maybe there's some salient covariates, like how do you know that the model is specified correctly to just end that, right? Because this is unadjusted.
Yes, it's completely unadjusted.
And it's also not parametric, so you haven't run this through any modeling approaches, what the data look like. Just plot it out.
And so that would be sufficient to say just.
If in a perfect world, if you had an ideal, if you had perfectly randomized groups, if there was nothing weird going on with the randomization, and the randomization worked, people think, oh, well, I randomly allocated people to treatment and control, so they're fine. But it's usually a good idea to check your covariates to make sure that, well, just because you randomly allocated doesn't mean that by weird sampling error, one group is older or one group is more males than females. So usually you want to check that. But in a perfect world, if you run it and everybody is sort of evenly distributed across the two groups, if you are confident that the only difference between the two groups is the treatment, this would be a fine way to, log rank is a fine way to analyze your data. And I've actually seen that in academic manuscripts. And the nice thing is you're not imposing any model structure or functional form on the hazards or anything that we're going to talk about later. It's just a straightforward statistic. There are a bunch of variations on the log rank test that take into account differences in ties, if you have ties. There are different weighting functions for over time. Over time, you're losing data. The denominator, the number of people left, is shrinking. And so your confidence band, if you imagine that, is getting wider. And so there are different weighting functions for the log rank test that give more weight to later times and even it out. There are a lot of variations on the log rank test, but it is a way to do it if you have perfect data, perfect design.
Well, I like the addition of making sure that the covariates are, randomly represented and stuff.
Yeah.
But I mean, if you have a table 1 with your demographic characteristics, another important salient, and you start with that and you say, look, it's a large enough sample, variability is narrow, means they're balanced in the means.
Yeah.
That's usually what I like about it, sort of like the underlying meat and potatoes of the non-parametric approach is so it does it every period that you have in there. So it compares treatment control at every period, like a Wilcoxon text in there, each one, and I can't remember if it like multiplies period over, it does some sort of a weight averages, I can't remember what it does.
Yes.
Right?
So over time, you're losing the denominator, right? So if we go back to one of these Kaplan-Meier curves.
The one where there's,
actually the survival table.
That one is really good too.
Here's the beginning. If we look at these tables, actually, let's just look at this one. Here, there are 312 people in the denominator. So 22 out of 312 people failed. So in the beginning, we have 312 people that this is based on. But by year 10, we have 3 people out of 32 failing. And so we can still calculate the survival. But look over here at the confidence intervals. They're going to start getting wider and wider. See up here, they're 0.89 to 0.95. It's really tight. But once you get down here, now it's starting to get wider. And the reason it's getting wider is because our denominator is shrinking as we go farther out in time. And so what all these different weighting functions, Wilcoxon and these other things, is they give different weights. You could actually reweight these so that you could even them out. Or you could give more weight to the test statistic at the beginning where you have a larger sample and less weight to the end because you have fewer observations there. So there's a whole literature on these variations of the log rank test that have to do with the weighting. It's just a weight multiplied times.
And it's really cool. And so in Stata, there's a bunch of options. And another one, there is, I can't remember which test it is, but you can do it if there's multiple treatments.
Yes.
I can't remember which command it is, but it's very similar to this. And so it's nice that you can relax any sort of distributional assumptions on it and let this go. Again, of course, you're assuming that your groups are comparable or equivalent, right? That's where the things break down is if you've got observational data.
Yeah. I'm sorry, was there another question?
That was my question. When do you use non-parametric tests?
When you have a perfect world. Yeah.
It's funny because I was like you, I was like cost regression period.
Yeah.
So you were broadening my horizons here.
Oh, good. Well, I'm glad, because literally when I started teaching this at A&M, this was a nuisance as far as I was concerned. I blew past this. So we could get on to the good stuff, which was Cox regression and time-dependent covariates and all this stuff. And it was only later when I started doing contract work for the Texas Health Department. That's not their name, but whatever their name is. I was shocked. They do a lot of live tables, and they do a lot of this stuff that's just fairly basic non-parametric stuff. And then I was at the World Health Organization website one day and started looking at their stuff, and they publish a lot of live tables. And so I started thinking, wow, I'm doing a real disservice to my students by blowing past this and getting onto Cox, because not everyone works in clinical trials. It was a personal bias of mine because that's how I had come to survival analysis and used it in the real world. But so I'm glad I've made that point to at least someone that this is not something just to blow past and ignore as a historical novelty, because I know it's not cool anymore. You're not going to go to the ASA and hear people talking about log rank tests and weighting schemes anymore. But it is a useful thing, and it does have an application out in the real world. And the calculations are fun, especially when you color code them. But again, we're going to skip over that. Where are we? Okay, semi-parametric estimation. How are we doing? We're doing great on time. Semi-parametric, Cox regression, one of the most famous papers in all of statistics, Cox's 1972 paper that introduced this. By the way, in that 72 paper, he also introduced what do you call it, discrete survival analysis. And I didn't even know that until I had a student working on her dissertation. And it had been years since I looked at the paper, and she referenced it as for her discrete stuff. I'm like, what? So I went back and looked, and sure enough, he also kind of introduces discrete time survival in this paper as well. But we're going to focus on Cox regression, probably the workhorse of all of survival analysis. It's called, well, we'll come back to why it's called proportional hazards in a minute, but and semi-parametric. But it's easily the most popular. I think I'm on safe ground saying that's the most popular way of analyzing survival data around. In Stata, if we wanted to do the equivalent to that log rank test that we just did, we could type stcox rx, no log. It just tells Stata to suppress the iteration history of the log likelihoods, makes the output look a little cleaner. So that's all the no log option is there for. And so we run our regression model for Rx. We see that we get a hazard ratio of 0.94, p-value of 0.75, and so that suggests that there's no effect here as well. But now I just used a bunch of terms that I'm not sure you're familiar with. What is a hazard ratio? What are some of these other things? So let's back up and talk about what is even a hazard. So hazards or hazard rates, it's the probability that failure occurs in some little sliver of time. Between right now and just a minute later or 30 seconds later or whatever, what's the probability that failure occurs in that interval of time as that little sliver of time goes to zero? So let's look at a picture and see if this makes more sense. So I'm interested in the time between time t and t plus delta t, and I want to let delta shrink, delta t. So does failure occur in this interval? Does it occur in this interval? Does it occur in this interval? Does it occur in that instant? Okay, and that's what I'm interested in, is instantaneous risk, instantaneous probability of failure. So I'm going to refer to that as a hazard or a hazard rate. Now, a hazard rate is in units of time. It is a rate. Rates are usually done as something, a number of failures per unit of time. And so you can actually multiply these things by t and get probabilities back. So it's not hard if you think about that equation. If I move delta t to the other side, I get a probability back, right? So if I take my hazard rate and I multiply it times 1 year, then I get the probability that the event occurs in that year or 2 years or 3 years or whatever. So there is a relationship between a hazard rate and a probability of failure. So to go back and forth between them, we're going to need to define what that sliver of time is with the denominator. But if you get confused about what is a hazard rate, just think of it in terms of it's the probability of failure in some little sliver of time. Okay? So, for example, a hazard rate is 2 per day, 2 events per day. Then the hazard rate is such that if blah, 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 we would expect 2 failures in an entire day. Or you can convert this to exponents and do some other things. But again, it's a rate. Now, there's a relationship between the hazard rate and the probability. There are all these other functions that people refer to in survival analysis. There's the survival function, which is this capital T. There's the density function, which is the little f of t. There's the cumulative. We're not going to focus on a bunch of this stuff today. That's stuff for a class, and it's a bit much. But I do just want to point out that you see these different equations, but there are different ways of writing them, and they're all related to each other if you dig into this a little bit deeper. Now, Cox regression, what we're going to do with that is we're going to specify some baseline hazard rate. For the overall sample or population, whatever, what is that baseline hazard rate? How many events do we expect to occur in some unit of time? But we'd like to adjust that hazard rate for covariates, for whether you're male or female or treated or how old you are and those sorts of things. So we have this baseline hazard rate, and then we have a model part which increases or decreases that baseline hazard by a certain amount, and that's this modeling part. Looks kind of like logistic regression. Now, it's typical with Cox regression to move the intercept term inside and sort of bundle it up with the hazard rate, the baseline hazard rate. So typically we see these without an intercept. Okay? You're not going to see intercepts with Cox regression, and that's why as we just move that part in and wrap it up with the hazard rate. The reason that we refer to this as semi-parametric is because we're not going to be picky for Cox regression about the functional form of this baseline hazard. We're just going to kind of ignore it, and I'm going to show you why here, I think, in the next slide. We're not going to be concerned with what is the functional form over time. Notice it's a function of t, which means over time that hazard rate could be changing. It could be different depending on what point in time we're talking about, but we're going to ignore that. The only functional part of this, or parametric part, is the model part, and that's where the term semi-parametric comes from. It's parametric in this part of the model, but we're going to largely ignore what the functional form of this baseline hazard is for now. Okay? So the reason that we can ignore what that baseline hazard rate is because usually what we're interested in is what are the effects of the covariates on that hazard rate. And when we compute something called a hazard ratio, the hazard rate, the baseline hazard rate, just cancels out. So for instance, if I have the treated group and the untreated group, in the numerator, I'm going to have the baseline hazard times e raised to the beta 1, whatever that coefficient is, b1, times 1 if the person was treated. And in the denominator, it's going to be the same thing, but times 0 if the person is untreated because it's a dummy variable, indicator variable. I'm trying to stop using the word dummy. For reasons of a story someone told me that they used in a talk and it didn't work out so well. So I'm trying to stop using dummy indicator variables. So anyway, if I write this all out, the baseline hazard rates cancel, so it doesn't really matter what they are. The thing I'm interested in is what's the effect of that covariate, and the effect of that covariate is e raised to the b1 beta 1 power. So that is what my hazard rate, my hazard ratio is. So I don't really care what the original hazard rate was. It cancels out. Was that the fourth time I've said that? It's important. So the hazard ratio is defined to be the hazard given that x equals 1. This is for a binary predictor, over the hazard given that x is equal to 0. Again, time cancels if we look at this. And so because the delta t, it doesn't matter what the interval is, what we're left with is the probability of failure in that sliver of time given that they were treated over the probability of failure in that interval of time given that they were not treated. That is a ratio of probabilities or risk. What is risk, right? Risk is just a probability of failing in some defined period of time. So if it's a risk of failing over another risk of failing, it's a risk ratio or relative risk. I read that about 5 times to make sure before I put that in the slide because I've been waiting and no one has yet to do it in class. You guys are new, maybe someone will do it today. It is in fact a relative risk. It's a hazard ratio, but you could call it a relative risk if you want, okay? Or a risk ratio. So the interpretation then would be a hazard ratio of 1.5 indicates that a risk of failing for individuals with x equals 1, treated, male, whatever, is 1.5 times the risk of failing for individuals with x equals 0, placebo, female, whatever. Okay, so it has a nice tidy interpretation to it, which is partly why Cox regression is so popular. So in this case, the model that we ran before, we ran a Cox model with only drug in it, the Rx variable. We get a hazard ratio of 0.94. So the interpretation of this would be a hazard ratio of 0.94 indicates that the risk of failing for individuals who got the drug, Rx equals 1, is 0.94 times the risk of failing for individuals with Rx equals 0, people who didn't take the drug. So the risk is lower for people who took the drug than people who didn't. So maybe the drug is successful. Except if we come over here and look at the p-value, that suggests that it's not statistically significant. Maybe our sample size was too small. If that had a really large effect size, we might want to draw a larger sample and see if it holds in a larger sample. Maybe we got a large p-value because we just didn't have a large enough sample. We were underpowered. But in this case, who knows? Now, after we fit a Cox model, we can actually do one of these survival curves after the fact. This is model-based. It's based on the model that we just ran. It's not like the Kaplan-Meier curves that's non-parametric. It's raw. It's just a simple count. this is based on the model that we just ran, okay? And that's important because if we include other covariates, it becomes adjusted for that. So I can use the ST curve. Can you guys see the bottom of this thing? You can use the ST curve command after you put a Cox model to see the survival experience. Now notice that first off, they seem a little closer together, the lines, than they did when we ran the raw data by itself. The other thing is to me, they don't look like they crisscross as much, but I could be wrong because the lines are so close together, we might want to zoom in. But nonetheless, this is something that you can run after your Cox model to get a feel for the survival experience of the two groups. And you can do this with multiple covariates and adjust it for that. Now, one of the things that we assume when we run Cox regression, I keep calling it Cox regression, but it's actually called Cox proportional hazards regression, or Cox proportional hazards models. What that means is that the difference between these two lines is proportional over the entire span of time. That the vertical distance between those two lines is the same regardless of what point in time I choose. That's the proportional hazards assumption. Sometimes it's met, sometimes it isn't. And one of the things that I want to look at or check is that assumption met? Because if it's not, then this model is inappropriate and I need to go some other route. So in this case, I have a test I can run called EStat-PH test. That's the command. And it will test whether that proportional hazards assumption is met. And in this case, the p-value is 0.4766. This is a time when we don't want to see small p-values, because if we see small p-values, that means we have a problem and we'd have to deal with it. But in this case, we don't. Our proportional, we don't have any evidence that that assumption is violated. Any questions so far? Okay, let's take it. Yes?
How do you assess the fit of this model?
In terms of how well it fits the data?
My guess would be if you have competing models, like then I just
Right.
use AIC, BIC. I don't know, if you can use log likelihood ratio after?
Well, if you have nested models, so the reason I seemed a little stumped when you said that is you don't have an intercept. So if you ask that question about linear regression, where I would go with it is say I would run what's called an intercept-only model with just an intercept, and then I put drug in and do a likelihood ratio test to compare those. But in this case, we don't have an intercept, so there is no null model in the usual sense to run.
Do you know if EStat-IC works after?
EStat-IC should work after this, yes, because it's a likelihood base.
Yeah, so then in that case, so
you could do a likelihood.
Competing models, and then you find out which has the lowest AIC or BIC estimate.
That's an excellent question. I hadn't really given that a lot of thought. Just does the model fit the data? That's a good question. But again, back to competing models, you could do that with AIC or BIC, or if you had nested models, you could compare them with likelihood ratio tests. If you're familiar with likelihood ratio tests for comparing nested models. But because there is no intercept-only model to sort of compare this to. So that's a really good question. If you want to see me after and give me a card or something, I'll get your email address and look into it. Because for some strange reason, that's something I've never really thought about. But a perfectly obvious question. Okay, so continuous predictors. Binary predictors are easy. What are we going to do with continuous predictors such as age? So if I run my Cox model using age treated as continuous, I get a hazard ratio of 1.04. And my interpretation of that would be a hazard ratio of 1.04 indicates that the risk of failing increases 1.04-fold for each additional year of age. Okay, well, how did we come up with that? So let's go back through our calculation again like we did before. That hazard ratio is calculated as the hazard for someone who's, say, 60 years old compared to someone who's 50 years old. And the output is based on a 1-year differential, but here it's a little easier with the 10-year. So I could compare a 60-year-old to a 50-year-old. Again, the baseline hazards cancel out. The rest of this cancels out, and what we're left with is e raised to the beta coefficient times a 10-year interval. What's interesting about this is if I'm looking at a 60-year-old versus a 50-year-old, I could look at a 30-year-old and a 20-year-old, and I get the exact same coefficient. So this doesn't take into account whether someone is older or younger. It's going to assume that a 10-year differential is constant, whether they're 60 and 50 or whether they're 30 and 20. So that's something to take into account. That may not be a true thing, and you may want to interact this with time or do some other fancy things in your modeling if you have reason to believe that a 30-year-old versus a 20-year-old is substantively different than a 60-year-old versus a 50-year-old, because you're going to get the same exact hazard ratio depending on how you do that. So again, our interpretation for continuous variables, just sort of a canned sentence you could type, is a hazard ratio of 1.5 indicates that the risk of failing increases 1.5-fold for every 10-year increase in age. The output that you get is assuming a 1-year differential, but I would prefer to work on maybe a 5-year or 10-year interval. So again, this is the same slide we saw before with the one age assuming a 1-year interval. If you wanted to assume a 10-year time interval, you can use what's called the lincom command in Stata, which is short for linear combination. And so I can ask, what's the effect of a 10-year? So the command would be lincom 10 times age. And then the comma E form tells Stata, I want you to exponentiate the coefficient so that I can see what is the effect, what's the hazard ratio for a 10-year differential in age. So in this case, rounded, it's about 1.5. The hazard ratio is about 1.5. So this is the interpretation would be, like we said before, a hazard ratio of 1.49 indicates the risk of failing increases 1.49-fold for each additional 10 years of age, not 1 year of age. And you can do 5 years or whatever you want, whatever kind of differential. But keep in mind the default is a 1-year differential, just like an indicator variable.
That's because we specified that earlier, right?
Here I've done 10 years because I'm more interested in a 10-year differential.
Right, but in terms of the model itself, the scale?
The ST set is scaled at one year.
Right. ST set, that scale is 1 year of time for survival time. But here I'm talking about age.
Right.
Oh.
What's the effect of age? So a 10-year differential of age, not follow-up time, but their actual age that they were when we first saw them.
I get that. But I mean, just in terms of if I wanted to rescale this for the time, that's where I would do it. Is at the ST set and say, I'm not interested in yearly data. I want, 10-yearly, increments of 10 years.
Yes, but careful not to confuse the two. The scale in the ST set command was for the observation time. So were they followed for 12 years or 12 days, or what's the unit of measurement? Because you may have it measured in decimals. Somebody may have recorded years, but they did it in some weird decimal thing.
Yeah.
So you could tell it what the scale is. What I'm talking about here is the effect of age. So not the time they were followed up, but what is their age when I'm calculating this. So I could be comparing a 60-year-old to a 59-year-old, for instance. So they're two slightly different issues.
Yeah. I guess,
Scale wouldn't affect this. Oh, okay.
but like if I'm looking at quarterly, would that put it?
Maybe 4, depending on how the actual numbers are recorded in the data set. So you just, basically what the scale command is telling you what's the unit for the denominator per year, per month, per whatever. And if you change that, when you do things like incidence rate, it'll change the denominator so that you can scale it however you like. So, and that you would do that with the ST7 command. Okay, any other questions for semi-parametric before we move on to parametric? Nobody's run out so far. Yes.
Is there a way to find a cut point for using Stata? For example, if the instant for my analysis is that I'm looking at patient prescription, how many days they were prescribed, and up to a certain point, when will they come back for the refill? And that's my instant I'm looking at.
When they come back for the refill?
Yes.
So that's what, and if they don't, then they're censored. So you want to
Yes.
say time to event is when they refill.
Yes. Yes.
Okay.
So for SAS, they do have those macro for us to download. I was wondering in Stata, is it possible to do that
For actually creating the survival time data? Is that what you're asking?
for actually find the cut point? But at what point, how many days?
The time, as opposed to the median time or the mean time until they
come
get-
back to.
So it's like so it is to give you, as opposed to the probability of filling it or not, but the actual
The median time until the event? Yes.
Yeah.
Yes. We're coming to that.
Yeah, okay.
You could,
Or even
Yeah, there's a way to do that with
model, you could
Cox.
do that too.
you could do it with treatment effects. I'm going to show you how to do it with parametric. And I had 91 slides in here. So I thought rather than show you every variation of all of these, particularly Cox and parametric because they're so similar. I'm going to show you how to do that with parametric, but you can do it with semi-parametric as well. Predicting the median, some people call it the median residual life and things like that. But you can predict that after either one of these, but I'm going to show you how to do it in parametric. So we'll get to that here momentarily.
Are you going to show the use of margins after these? Or?
Yes.
Okay.
This is perfect. You guys know right where we're going, which tells me that this is logical. It's in a logical order, so that worked out well. So let's talk about parametric, and we're actually going to get to margins and how to calculate median residual time or life or whatever here shortly. So parametric estimation, fully parametric, not semi-parametric. What we're going to change now is that we are actually going to specify a functional form for this baseline hazard. Notice that hazard rate is a function of time, right? And so these are some different kinds of functions that we might use to specify a functional form for the baseline hazard. Again, we're not taking into account any covariates at this point yet. If we just want to talk about the baseline hazard, is maybe after surgery, what's the probability that someone dies? Well, maybe after they have bypass surgery or something, the risk is really high right after, but then it goes down pretty quickly. If you survive the first week, you're probably home free. So there are a whole bunch of these different functional forms that you can use, Weibels and gammas and all kinds of things, log logistic and Gompertz, and it's a fun shopping experience shopping for one of these. Exponential is a special case of Weibel. But anyway, the point being, you might want to specify a parametric form for this. And there may be in the literature that in the area you work in, where there's a standard distribution that's used to describe this hazard. And if there is, you might want to go ahead and do this because there are some things you can do, such as smooth hazards and things, when you specify a fully parametric model. And I am not an expert enough on this. Somebody in this room may know this, whether or not you can squeeze more power. I think in most situations, you may be able to squeeze a bit more statistical power out of these because you are specifying an additional functional form, but you're doing that at the risk of making some assumptions about this functional form that may or may not be correct. I don't know that that's universally the case, that you would always have more statistical power, but it's something you might check into. And again, check into the literature in your particular application area, because there may be a standard like a Weibel that's typically used. And if you go running Cox models when everybody else is running Weibels, then you should have done it the other way. Anyway, the command looks remarkably similar to Cox. The command here is streg, and if I wanted to specify the same kind of model that we did before for the drug treatment, I'm just going to type streg rx, but then I do have to give it a functional form. I should have written out distribution, but I've typed comma dist, that's short for distribution. And here I've selected an exponential distribution for my baseline hazard rate. So I'm assuming that this drops off fairly quickly, the risk over time. Notice the output is a little different in that it has a constant. It does actually have an intercept. Underscore const is Stata speak for intercept. So this model has an intercept, and then it also has a hazard ratio. And again, the interpretation is just like we interpreted before. It's a hazard ratio. For parametric models, there is another alternative called accelerated failure time, and I don't want to put that in here because it seems to confuse people. But there is an alternative way of interpreting parametric models called accelerated failure time. But we're not going to talk about those today. We're going to stick with hazard ratios. And the interpretation is exactly like it was before with Cox regression. Now, we were talking about things you can do after. One of them is ST curve like we did before, but notice that these curves are nice and smooth. It's because we're specifying a functional form, so we can look at the hazard rates or the survival experience over time. I think in the next hour, we're going to see how you can do hazard functions and things with these. I'm only showing you survival curves, but you can do hazards and other sorts of things. But the point of this one is these are smooth. They don't have that zigzaggy thing going on because it's smooth because we have a smooth model. And the interpretation, I don't know why I have this slide in here twice.
No, this is
this is age. This is different. This is age. So again, the results are about the same. 1.03, 1.04 rounded hazard ratio, 1.04 indicates risk of failing, blah, blah, blah. You could do the same thing here if you wanted to specify a differential of age with that lencom command like we did before. Something else you could do is margins. So back to the question of how long the predicted time someone lives or waits until they have the event, can be calculated using the margins command. And here I've done it for ages 8 through 70 in increments of 10. So we can see that the older you are whenever you're being observed, the lower your average time you're going to live, which kind of makes sense because you don't have as long to live to begin with, but you're probably older, sicker, whatever. But you can predict the median or the mean, whatever you want, predicted average survival time from these kinds of models.
That answers your question.
Is that what you were interested in?
Yes.
Okay. So the actual time. And no, you can't.
Well, if you didn't put it at, then the margins would give you the median.
For everyone.
The median
Just
for everybody. So that would be, I think that's, if you don't care about, does it differ between this group and that group, you say, what is the median time till prescription refill? If you just did margins with nothing, with no comment or anything beyond that, it would give you your median time across the group. Or if you wanted margins at
by drug treatment.
Treatment, yeah.
Or sex
or
or
over treatment. Is it over treatment?
Over. Well, you put it in front of the comma.
Yeah, and then you'll have margins treatment, and they'll give you what your median time to fill the prescription is for one group versus the other group. And then
if for continuous variable, I can do like sensitivity, the ROC curve, and look at that. And for this one,
ROC curves.
I didn't think of that.
That's for the continuous or for.
Here, the age here is continuous. So
yes.
That's why. So he specified here
at particular time.
At a particular point, starting at 30, ending at 70 in increments of 10. So you can do the same thing if you have a continuous covariate that you're interested in seeing the distribution of the median time.
Okay.
Or the median probability.
The margins command works after just about any command in Stata to do predictions from your model. So whatever covariates went into your model, you can then calculate the predicted outcome, whether it's median time or whatever, based on, if you have continuous variables, you can say at certain points on the continuum, or if it's a categorical variable like sex or treatment or whatever, it will do that by separate groups. So if I had treatment here, which would have been, actually I did. Yes, I did it by treatment. So this is because I was thinking, gosh, that would have been a cool slide. And I guess I thought of that and put it in here.
That's a cool slide.
That's a cool slide. So this is the same thing over age at different age points for the treated and the control group. Okay. Now, what's interesting about this slide is that it's again showing that the time is shorter for the treated group versus the placebo group. Now, that may be because those lines crossed. Remember when we did the non-parametric, the Kaplan-Meier curve? The lines crossed. And that's another argument for going back and looking at non-parametric things. Because if I just look at these models, here I would look at this and say, the drug group is living a shorter amount of time across all age spans. It doesn't look good for the treatment. But if I go back and look at the Kaplan-Meier curve, remember in the beginning, and they crossed at about 5 years, that's much more interesting information because I haven't posed any kind of assumptions or models or anything else. So there may be a very complicated relationship between this drug treatment and time. If you make it past 5 years, the drug helps you. But up to 5 years, it may be hurting you, or it may not be helping you enough. So there may be a much more complicated relationship, and I don't know that much about whatever this disease is and treatment. But this model is almost certainly oversimplistic, and we want to take into account more things in this. But the cool thing is with the margins command, you can look at these sorts of things. You can make predictions from your models. And you can do this after almost any command in Stata, regress, logit, Poisson, negative binomial, whatever. Okay, I'm glad I put that in there because it was a cool slide. So,
and comparing models.
Yes,
that answers the earlier question.
Right. So with parametric models, one of the issues that comes up is what parametric functional form should I use for my hazard? Should I use exponential, which is the easiest? Should I use Weibull or whatever? What I can do is I can run these. The first thing I wanted to show you is just the table of the estimates. So I've run this with the Cox model. I've run this with an exponential, assuming an exponential form to the hazard rate, and hazard function, and a Weibull, just so we have some points of comparison. And if I look at the parameter estimates, there is no constant for Cox. But the effect of drug treatment, this DPCA is about 1.076. For the Cox model, it's about 1.088. For the exponential, it's about 1.089. Well, 1.9 if you round it for the Weibull. They're not terribly different. Age, the effect is 1.04, 1.04 rounded, 1.04. So in this case, there's not a big difference between these. But if you don't have any idea, if you're off in the Wild West with these parametric models, choosing a functional form is going to be some added work. You're going to have to explore that what is that function. You could do these either using AIC. So after you run any of these models, for instance, here I've run Cox, exponential, and Weibull. I don't think it's fair to compare Cox and the parametric stuff using AIC and BIC. That doesn't make sense to me because they're just fundamentally different things. But comparing exponential and Weibull, it looks like the exponential model actually has a slightly smaller BIC. Well, the AIC is smaller for Weibull. BIC is going to penalize it. Anyway, it doesn't matter. These are kind of close. You could probably use either one. But another way you could compare exponential versus Weibull, because exponential is a special case of Weibull, they're nested models. I could run a likelihood ratio test and compare those, and this p-value of 0.09 suggests that the exponential model might be fine. Having that extra parameter for the Weibull may not be necessary. Okay. But again, choosing among different parametric forms, we got to wrap up, is an extra thing you're going to have to do with parametric models. Okay. So that's kind of where we've been. References, obviously that Stata Press book. I need to update the date on that. And these are some of my other favorite books. We also have an entire playlist on our Stata YouTube channel that shows how to do pretty much everything I just showed you here. I don't know how much parametric there is.